Hello. So today's topic will be Riemann bilinear relations. I think it's necessary to explain it today. What does it mean? Assume we have a Riemann surface gamma. Genus 2. Two basic cycles, A1, A2, and two basic cycles, B1 and also B2. So, with basis in homologies, with two G basic cycles, A1, AG, B1, BG. After cutting the Riemann surface along these cycles, we obtain a polygon with a 4G gon. Here it will be octagon. A1, B1, A2, B2, minus 1. It's full octagon. And assume we have a pair of differentials. Omega 2. Assume that is equal to 0. Two closed differentials, omega 1 and omega 2. Then we can introduce the following scalar product on the space of differentials. Can we introduce it? So you simply integrate this wedge product. Is it necessary to recall wedge product, or it's assumed to be known? Wedge product. Now we can assume the following. Assume that the point will be P0. But it's not important. Assume that we are inside this polygon. Sorry, may I open the window? Because I'm sorry, but if you don't mind, I need some air. Don't mind. It's okay. So, first of all, of course, we don't assume that this form omega 1 is not necessarily exact on the Riemann surface, you understand. But inside the polygon, we can find the primitive. F the gamma, f of gamma, omega 1. And we assume that integration path lies inside the polygon. Okay? But of course, the function, formally the function f is defined on the Riemann surface. but on the Riemann surface is discontinuous, you understand? Because the values, for example, here and here are different. Therefore, it's a function which is discontinuous. Its discontinuity is on the A cycles and B cycles. But inside the polygon, it's a well-defined function.
Why discontinuous?
No, okay, consider the simplest case. Okay, 0, 1, I. This square, simplest case, Riemann surface. Omega is dz. Agree. F is z. So the function of the torus. Here, function is I, y, you agree? Here. Here is I, y plus 1. So if you make a torus, we have two cuts. Okay, the point 0 will be here, or have two cuts. Therefore, the function, okay, the function here is I plus 1. Do you agree? I plus 1. How we obtain the torus? We glue these sides and we glue these sides. Therefore, this point is 0, and we see the function here, I'm sorry, from opposite. I and 1 plus I. Here function is I. This is this one, you see. But this point is this one. Sorry, is it clear? So the function is multivalued. Not multivalued, but discontinuous. It's discontinuous. With discontinuity on the cycles. Therefore, we have here. Now, we can write the following thing. Let's apply Stokes formula. Gamma equals to you agree? You have the Stokes formula. The Stokes formula was defined in your lectures. Because, of course, the F omega, it will be you agree? Of course. You agree? By Leibniz rule. And then we have its closed form, therefore we have only this term. So far, so good. Awesome. Okay, let me keep the it's 0. No. Therefore, let me write explicitly. Therefore, it's integral over A1 B1, sorry. And so on. You understand, we have 8 terms. You mean integration over this, over this, over this, over this. But what we have? Let's know the points gamma 1 and gamma 2. U3. Therefore, the first two terms can be combined in the following form. E1, it will be E2, I3, I4. So we can rewrite I1 plus I3 over A1 So what I did, I considered a pair of closed one forms. And I consider the four-n-gon. I took a compact Riemann surface, I cut it along the cycles, the four cycles, therefore I have a four-n-gon. Now, I consider this following form on the Riemann surface. And I do all calculations inside the n-gon. Both forms are assumed to be closed. Therefore, inside the n-gon, not on the Riemann surface, but inside the n-gon, we can define primitive. Omega 1 is df1. Can assume that we start integration from point 0. It's not essential. Therefore, we have the following. Now we apply the Stokes formula. Because her and her, omega 2 is the same, you see, is the same form. But f are different, you see. But what does it mean? F of gamma 1 is integral over b1 omega 1. You agree? Because this is exactly B-cycle. It's homotopic to B-cycle. Therefore, you have the following identity. F of gamma 2 means f of gamma tam is, therefore, we obtain that E integral minus integral of Okay, so is it clear? Is it okay? Because this difference is a constant. Therefore, this is constant times this integral. I think it's not necessary to repeat. I2 plus I4 is integral is equals to sum from k equal to 1 to g bk minus integral So So we obtain the following identity. Okay? I think the calculation seems standard and trivial, but let me explain that it implies very non-trivial consequences. Okay? First of all, assume that we have two basic forms. You remember, you have canonical basis of forms. First, omega delta h. Okay, for example, we have this integral. Okay? We have this base is called IK. JK. Yes. It's called canonical basis of holomorphic forms. Let's apply this integral. In local coordinates, omega k dz, therefore, is a zero form. You see, dz, h dz is zero because it's Q symmetry. Therefore, this is equals to zero. But you may tell that it's trivial that we have zero integral. But let's calculate it using bilinear relation. Integral over integral over omega k. Agree. I wrote the bilinear relations, bilinear relations, you obtain that it's by G you obtain this. Simply use the definition. Therefore, we obtained here BL from UK. Sorry, are there any questions? You simply applied, it's rather trivial relation, and you apply this relation to this pair of differentials. Therefore, we obtained the following identity, that where BKL is integral this is called the Riemann matrix. The Riemann matrix. Then we proved theorem, we proved it. Riemann theorem. That this matrix of periods is symmetric. Okay, you agree. It's important and not very trivial result, but it was obtained from this. The proof is elementary, but the consequence, I think Riemann understood it. You see, this matrix is symmetric. It's important. The second property. Consider the following integral. It's now non-zero. You see. We have scalar product, a Hermitian scalar product on the holomorphic differentials. You agree? And what we know that for any holomorphic differential, only keep this. For example, you have holomorphic differential omega let me write it dz in local coordinates. Then is something non-negative, and it's positive almost everywhere. Times no, okay. Maybe this scalar product, it's not very important. Divisors. Therefore, this scalar product always real, and it's positive if form is non-zero. You see. It's great. It's first of all it's real. Greater than or equal than 0 if it's 0 if omega is 0 form, if omega is non-trivial form, it's positive. You see. So we have well-defined Hermitian scalar product. And the matrix of this Hermitian scalar product is B. But what we obtain here You agree? But it's symmetric. So 2 times 2i in BKL. You agree? Okay? So is it clear? Is it clear? We simply apply to this pair of forms but what does it mean? It means that the imaginary part of the Riemann matrix defined a Hermitian scalar product. So it's positive defined. So we prove 2 properties. I think it's good. You agree? I think the proof is elementary, but you see. You agree. The imaginary part of the Riemann matrix is positive defined. No, maybe I will try to prove the Riemann-Roch theorem now, but but now let's continue. Now, next topic. Now we will consider only holomorphic forms. But we can consider not only holomorphic, but also meromorphic forms. Assume that we have 2 forms, omega So you remember we considered 3 classes of forms. Forms of the first, second, and third kind. First kind, holomorphic. First, omega, holomorphic. Second, the forms which may have poles, but the residues are 0. It's enough to consider basic forms. Basic forms, you can fix a point P1, and we fix, for example, some pole. This Z. You remember what? Consider such singularity. Then there exists a unique form. I make a reference to the Springer book, such that omega such that, first of all, use regular terms at P1. So it has exactly one pole. In this pole, it has this term plus regular part. And also, that all integrals over A cycles equals to 0 equal to 0 if the same. And third type, we have a pair of points, P1, P2. 1. So we have some Taylor series here, you understand? We fix the singular part, but we could not control the regular one. And the same condition. So you consider such differentials. Differential associated with some points, second type, and differential associated with pair of points, differential third kind. Now, second kind, differential third kind. Now, let's apply the Riemann relation, for example. I don't want full value, but assume that, first of all, omega 1 is holomorphic, and omega 2 second kind. What happens? Now we have this for n-gon. We have point P1, P0, and we can again construct the primitive. Where we use that we have zero residue. The primitive is well defined inside polygon, you understand? We don't have logarithms, we have no cuts. You remember that we will have 2 pi I F1 omega 2 is okay, you have the same relation. I agree.
What is, I don't understand what it says before, like, before the inequality.
Residue.
Residue, and before that it's
2 pi I.
okay.
2 pi I. Okay. So we apply the same formula, nothing new. First of all, it vanishes. I agree. No. Because of this condition. So second kind of the same will be the set kind differential. Therefore, you obtain for example, will be omega L from holomorphic basis. For maybe right F, not omega 1, but FL omega L. FLT. FLT will be from one of the basic differentials, this one. Therefore, it will be integral over B L. Or maybe it's better to use this notation, omega capital. Omega A. Omega A. Omega A. Okay? Is it clear? Therefore, it means that you don't even know the holomorphic one forms. If you'd like to calculate these integrals, can calculate these residues instead.
Can you repeat that again?
No, so we have these integrals. We sometimes require these integrals.
Sorry, integrals omega L by AK equals 0 follow
By definition, omega is the differential of the second. By definition, we consider basic differential.
terms
It's called what is
equals 0. No?
no. We have omega. Okay, let's note it. Omega. Integral over all A cycles.
Okay.
We use normalization. For the differential of second kind, all A integrals are equal to 0. You agree? Okay? It's by definition. We normalize this. Of course, we can add to this differential any combination of this holomorphic. And we so to fix an unique differential, we apply this condition. This condition fixes unique volume. Okay. But what does it mean? So assume that we have local coordinate power n. Omega omega. Is that consider the Taylor expansion of omega at this point. You agree? F. We obtain F is C0 plus you have the following expansion of the function f. You have Taylor expansion. The form we obtain that residue is okay. Okay, I hope. So we prove this interesting formula. And now consider the last. Assume that we have such a differential. What happens? Okay, let me remove it. And we consider what happens with the last differential. In the last case, we have the following form. We have 2 points. P2, P1, P0. Now, omega P1 at P2. We agree. Plus something regular. Therefore, now to obtain a single-valued primitive, we have to draw a cut from the point P2 to the point P1. And now we have to integrate, if you deform the contour integral, we see that we have integral over this path, you agree. But what happens? No, I'm sorry. I prefer to do the opposite. We have the form, it applies the same, and okay. No, we don't need nothing, because now we see that this integral, I'm sorry, no need to draw cuts, because we take primitive of the holomorphic form, omega. So we have 2 integrals. So this integral will be 2 pi I omega P1 minus res plus res and P2. You agree? So it will be 2 pi I f at P1 minus f at P2. You agree? You have this formula, so it's not a problem to calculate the residues. But of course, it can be written 2 pi I Да. Ой. Okay. So finally we obtain that integral of omega from P2 to P1 So you see, you obtain the following relation.
Why
BL, of course. BL. I'm sorry, BL, of course. So we prove the following theorem. So we prove the following identity, and we proved the following identity. You see? Okay? Sorry.
I mean, so we prove that 2pi residue FL omega. So, I mean, the sum is.
Integral, this, we consider this contour integral. It reduces to this two contour integrals. So this integral is equals to this. But it also equals to this. We apply the residue technique to calculate integral. Integral over the boundary is this one.
So there we had, I mean, there was different. Yes.
Sorry.
In the previous statement, the omega was different.
But the argument is the same. It's, the calculation is valid for both.
sorry, this omega general.
No, because in this calculation, if you replace from the third type differential,
Yes.
this the answer, the right hand side is the same.
This omega is
Third type.
normalized?
Yes, this is normalized. Okay, this first was omega has these singularities plus integrals over ak of omega is equal to 0, 1, g. Yes, of course. We have this. We're talking about normalized differentials. Yes.
Omega normalized for this. Okay. This formula this omega no equal.
Yes, there are two. Yes, two different. Yes. Okay.
And this formula
This is for third type. This is for the second type. We have two formulas. If you have differential second kind, then you have these formulas for differential second kind.
equivalent this formula in second.
And if you have the of the third type, it's slightly different. Instead of residue, you have integral.
But in second type have equivalent formula.
Yeah. Slightly different formulas.
2 pi I,
Yes.
2 pi I equal integral BL. Okay.
Two different formulas, I'm sorry. For the second type, you have residue. And for the third type, you have instead of integral over the path. But two different formulas, but now, let me prove the following. Let me prove two lemmas, nevertheless. Lemma 1. Assume that we have some collection differentials of the second and third kind. We have collection of points, P1, Ps, and we have two pairs, Q1, Q1, 1. Q 2 1 Q P 1 Q P2. We have some collection of points, some collection of pairs, and we have, of course, at each point we also put some. So it defines subspace. You defined PS. And we have points P1 and 1, PS and S. So assume we have some collection of points. Q1, Q2, Q1, 1. We have some collection of points. No, maybe I slightly different notations. QP. Okay, may I change notations? QL, B1 and 1, P, S, and S. Have some collection of points. QL, and you have points P1 and 1, PS and S. What does it mean? And consider the space of, and no, I'm sorry. Sorry. Let me. Yes. Q1. Okay. First of all, sorry. Let me prove the first limit. P1, PS, P1, N1, P1, Pn, Ps, and S. Okay, collection of points. And consider the collection of no, but we need some extra formula. Assume that we now have a pair of differentials. Omega 1, omega 2, omega 3. You can apply bilinear relations to such a pair. Omega 2 is a differential with some point at point P1. Okay, that's another version of this linear relation. What happens? Assume that omega 2 is differential of the second kind, omega 3 is differential of the third kind. Therefore, omega 2. Okay, first of all, let me remove it. Here pair of differentials. Omega 2. First of all, what's omega 2? May I use this notation so you understand it? Let's Q2 and integrals okay, we have such pair differentials. Then, the right-hand side of the bilinear relation is 0. Therefore, we obtain two pi I plus the point P1 equals to 0. You see? Because on the boundary, all terms are 0 because so we remain. Yeah, we have this identity. Now, maybe it's enough now. And now let me do the following. Assume that we have points P1 and 1, PS and S. And also let's point Q. 1, Q, L. We have such collection of points. First of all, consider the space of all differentials of the second kind. Let's introduce the space L1. L1, let's introduce such vector space. What does mean space L1? You have points P1. For the point P1, you have differentials. Let me note omega 1, 2, terms. Two. For all k. First of all differentials, all of them are differentials of the second kind. You agree? They have, and they all have zero A periods. Consider such a space. Dimension of the space is n1 minus 1 plus ns minus 1. You agree? You have such, and consider the space generated by all these differentials. And also, consider such space differentials. Theorem. Space L1. Let omega belongs to L1. So consider is such differentials linear combination such differentials. And consider the following pairing.
Could you repeat what is the space L1?
We-
It is the space of two,
We have n s points. At each point, we write an order, 2 or greater. For example, consider the simplest case. You have 2 points, P1, and then 1 is 4. P2, and then 2 is 3. So we consider the following for, first of all, differential, omega 1, 2, have dz plus regular terms. And of course, all A periods are 0, you remember. Cube plus regular terms, omega 4, 1, regular terms. Also, we have omega 2, 3 is dz z minus p2 cube plus regular terms. So you have 5-dimensional space. All linear combinations of these differentials. And of course we have this condition.
It's forms of second kind with
Yes, all of them are
prescribed.
second kind. But with singularities non-higher z. Non-higher z. Then, well, okay, may I remove it? You clear? Also touch space differentials. And we have the following pairing. Assume that you have simply then what is the condition? Ничего. If some primitives, you remember. You see, so we have the, you understand, you prove this lemma. And now the question is the following. Assume that we would like to construct meromorphic functions. Now, let me return to our main problem. We would like to construct meromorphic functions. Usually, you consider the following linear spaces. You have a, okay, let me introduce now divisors. What does mean divisor? Assume that we have a collection of points, n1. We have a collection of points, gamma 1, gamma k, and 1, and k integers, integer numbers. Some integers. So, formally, divisor, to start with, I will, in the first approximation, the divisor is a collection of points counted with integer weights, positive or negative. Then if you have divisor D, you write D. So you can consider a formal group generated by points, you understand? You know this construction. You consider points. You consider formal group generated by formal sums of these points.
So could be a billion group.
A billion group. Only, of course, sums are only finite. That if you have a divisor, you can associate a space of functions or a space of forms bounded by this divisor. Now you have divisor, points gamma 1, gamma k. Then we consider L0 of D. L0 of D are holomorphic for L0 of D. Okay, what does it mean? The space of meromorphic function on our Riemann surface. With the following properties. First of all, they have no poles except points gamma k they have the following constraint. The only possible position of poles are the points gamma k such that nk, ns, gamma s such that ns are positive. Of course, if ns is 0, we don't care about the points. And I will always assume to be non-zero to obtain a bit group. Is it clear? Therefore, if ns, so they have the following constraint. They may have poles only at the points gamma k with ns with positive ns. And the terms and at the points and at such point, let me remove it. Have such points, you have point gamma s, and then Taylor series, Laurent series is form at ns. Okay. Nothing. Therefore, we have only finite number of Laurent terms. And this number is restricted by ns, you see. For example, it may have no pole at all. It's permitted. You see. It's inequality, it's not equality. You'd like to have, like, you remember, in the theory of polynomials, we consider polynomials of degree not greater than n, you remember. Why? If you consider polynomials of degree n, they do not form a vector space, you remember. Because you have two polynomials of degree n, we add them and we obtain a polynomial of low degree. You agree? Polynomials. But if therefore we have to bound the degree but not fix it, you remember, to obtain a linear space. Again, we have a linear space of functions. We put the following constraint. We have Laurent expansion. It may have infinitely many positive terms, but the negative terms are not higher than ns. Minus ns, if ns is negative. And the second property, if ns is greater than 0, the same constraint. Maybe no, I'm sorry. Maybe it's opposite direction, minus. It will be of ns. If ns is greater than I'm sorry, it has a zero. At least minus ns. So here we assume if ns is negative, we permit poles. If its net is positive, we require that we have a zero. But of course, if we require zero of the second order, it may be zero of fifth order. It's permitted. But it's not permitted to have first order zero. If n is equal to, you have zero of the second order or higher order. It's an equality again. So the pole not more than, and the zero not less than, you understand? You have this upper boundary. Therefore, if we have a divisor, we have associated space of functions. First of all, assume that all n are negative. How to construct functions with such divisor? How to construct space of functions which are bounded by this divisor? The answer is the following. We consider the differentials with n1 minus n1 plus 1, space of differentials. So assume that all n Okay, how to describe the set, how to construct such functions? First of all, we don't know about existence of functions, but we know we have existence theorem for differentials. You understand the difference? For differentials, we have an existence theorem. For function, we don't have this moment. So what we can do? For example, first step, assume that all n1 and s less than 0. What we know about differential of the function? The function belongs to space L1. Remember the space L1. L1, I suppose, with the following properties. Gamma 1. Minus ns. You understand? No, first of all, the differential of the function belongs to the following form. If it has second order pole, its differential may have third order pole. You see? You see? You agree? Is it clear? As soon as you have function with belonging to such space, what you know about differential? If c minus 2 is square, let's have function. Consider what is the differential df? df is c minus 1 You agree? Okay. Therefore, we know the from the space of differential. But what is the constraint? What is necessary and sufficient condition that differential is differential function? All b periods are equal to 0. Agree. Is okay. So it's clear. That's the condition. So what is the space? So how to construct a holomorphic function? We consider such differentials and impose constraints at integral is equal to 0. Therefore, if all n are negative, we have the following description of the space of how to construct function. First of all, we have one integration constant. We agree. Then we have to impose this condition. But this condition is equivalent to the following one. We proved it. Okay, we can exchange. So, for example, you agree. Moreover, we don't know the number of equations. You can tell any equation, but for some spaces they may be dependent. We don't know if these equations are dependent or independent. But these two systems of equations are equivalent.